one of the pioneers of many aspects of theoretical RL. He's been working on this for a very long time, actually. And one of the things that he's heavily known for is trying to develop interesting notions of complexity to measure the sample complexity of RL processes. And you might say, well, RL maybe sounds like it could be a little bit of a stretch for a distribution shift workshop. So first of all, the answer is it fits. And second of all, actually, I haven't seen his slides or the abstract, but it's very common in all of the talks I've ever seen by Nangiv that he gives a distinct distribution shift flavor in all of the talks. Like I'm actually expecting you to use the terminology. So, so we'll hear a lot about distribution shift.
All right, thanks, Matus, for the introduction, and thanks, everyone. So as Matus mentioned, I'm a RL theorist. Throughout the talk, you will see like RLHF for LLMs and as examples, but I have to admit, like I know literally nothing about RLHF and LLMs beyond the most generic level. And later speakers like Wei or Lo, like 100 times better than me. But I think the kind of problems that we've been studying recently in RL will probably like resonate to some extent with some of the challenges that we encounter in modern large language models, and especially from a theoretical point of view, how do we understand them? Okay, so the theme of this workshop is generalization, right? So let's just do a super quick overview of what everyone knows about, right? So there's a very standard and traditional view of generalization in prediction tasks, and particularly like, for example, in a supervised learning setting, right? So suppose you run an algorithm, like just a classification or regression, and you can ask, does the algorithm generalize, right? And the theoretical understanding of it is like, it can be tricky and nuanced, but practically there's something super easy that it can do that you can just answer this question, right? You split your data into training and test, run your algorithm training, you get a classifier or a regressor, and just calculate its test error, right? And if the test error is approximately the same as the training error, you say that the algorithm generalizes, otherwise it's not. It's that simple, right? And we have some degree of understanding of what happens, like at least in the most standard textbook explanation. Generalization happens when you have a sufficient amount of training data that exceeds essentially the capacity of your function approximator, right? And of course, like traditional notion of capacities like VC dimension, random market complexity, and so on, may be a little bit outdated at the era of like deep learning and large language models, but still more or less the moral of the story still holds. Okay, but what I'm interested in is, I do RL. I work in reinforcement learning. So in reinforcement learning, you can ask a similar question, right? But before that, we have to, think about, where do you do reinforcement learning, where it begs the question of generalization, right? So in the setting I'm interested in, we also have data, but these data are generated by having decision makers interacting with the system, where the system could be, the dialogue system where you have users interacting with a chatbot. It could be, like, say, computer networks where the decision makers are, some kind of, for example, the routing decisions made by your routers, like base stations and so on and so forth, in a network. Or it could be like, treatment decisions or intervention recommendations offered by, software agents, like in a Medicare scenario, right? So in all these cases, these systems generate data. And the question is like, and the thing we are interested in doing is that we want to develop better decision-making strategies that optimizes the operations of these systems, right? And if you think about, how generally people do that, as I've been alluding to, this is what RL is about. But, if I just tell you this, it's not the most familiar form of RL that people are work with nowadays, right? So what is the most familiar form of RL people work with? It's like you have some kind of a simulator, like a video game or like board game or anything, where the simulator sits in your computer, right? And you can run anything you want, like PBO or like deep RL, all these algorithms just inside the computer and get an agent. So how does this connect to that familiar form of RL? Well, you can do something pretty simple, right? You can fit a simulator from data, and now you can just like use any kind of algorithm you like in the simulator. There's like tons of off-the-shelf algorithms, and then you train policy, right? So here, policy is a decision-making strategy. But now we have the question again, like how do I know that the algorithm generalizes, right? And practically speaking, that comes down to the question of how do I know if this policy is actually good or not? Now, you might ask, there has been like decades of, at least 2 decades of research on deep RL at this point. And what does people do every day? Well, in deep RL, like everything is done in simulation, right? So what you do is that you essentially just put the policy back in the simulator and just run that policy and see how it works. This is extremely cheap, extremely efficient. You can do it easily, except that in these kind of decision-making scenarios, where eventually you have a real environment, this evaluation doesn't necessarily tell you the truth, right? Because the simulator is fit from the data, and which may not be, fully accurate, right? So this is a question mark. So really, like the only sort of ground truth, the evaluation methodology you should use is actually A/B testing. That you actually run the learned strategy in the real system and see how it performs, right? But the problem is that although this is gives you a high fidelity of the evaluation, it's not always available, right? Because as I also mentioned like a little bit later, evaluation is actually the basis for optimization, right? So when you're doing optimization, when you're doing learning, like a common framework is that you're implicitly evaluating every single hypothesis and optimizing based on your estimation of how good each hypothesis is, right? So either explicitly or implicitly, you'll be evaluating thousands or exponentially many hypotheses, and apparently you can't afford to just to run each of them in the real system, right? And in many of the systems we're thinking about here, like edge networks or Medicare scenarios where the environment includes human patients, sometimes customers, students, and so on, you just can't afford to run a bad policy in those systems. Right, so okay, so if this is not something you can do, then it seems like the best possible thing you can do is to actually just take the data that have been generated from the system and try to use the data to evaluate how good your policy is, right? And in RL terminologies, we call that this problem of policy evaluation because there is a very obvious challenge that the data is generated by making certain kind of decisions, and the kind of decisions you've made during data collection. The policies you followed over there is generally different from the policy you want to evaluate, right? For example, let's say during data collection, I always turn left, and I'll ask the question, what happens if I choose to go right? Well, that's a very difficult question to answer. So, the talk today, I will be generally, focusing on this problem, and we'll see, like, I'll go back and forth between these two questions of when does a learned policy generalizes versus how to actually evaluate a learned policy. And we'll see like, these two questions are actually interrelated. Okay. So as a concrete example, using a scenario where like the audience of this workshop may be familiar with, we can actually cast something like a reinforcement learning from human feedback into this framework, where typically, you have data, which is like preference data that consists of prompt, pair of responses, and a feedback signal of like which response is more preferred. And for the purpose of this talk, I'm going to simplify it and just say we have the data in the form of prompt, response, and a numerical reward that scores how good the response is. And the simulator in this case is simply a reward model that predicts the conditional expectation of the reward given a prompt and response pair, right? And after you have the reward model, we all know like what you can do, like you can run PPO or any of your favorite algorithms to train a policy. And here you have the question, how does this policy actually generalize, right? Is this policy actually good, right? And apparently the thing you shouldn't do or you shouldn't fully trust is to just plug this policy back into the reward model and see how it performs. That's not going to work. And the reason is because, okay, so we'll talk about that later, but there's another option that I didn't mention in the previous slide, which is I can also just fit the simulator based on data, right? And maybe I can do hyperparameter tuning model selection in this phase and choose the best simulator based on the data I have. And the question is like, is that good enough? Well, it turns out that that's not necessarily going to work either. And this gets to one of the central themes that we were trying to get to in this workshop, which is distribution shift, right? So typically what happens in practice is that when you fit the simulator or reward model from data, this data is generated by a certain what we call behavior policy or logging policy, right? And therefore, even when you do model selection and everything based on this data, the reward model is only guaranteed, or you can only reasonably guarantee that the reward model is accurate for responses generated from that policy. And in fact, there are experiments others have run that show that if you have policies that are very close to the behavior policy, your reward model is accurate. But as your policy goes further and further away, if you consider a policy you want to evaluate, and when it becomes further and further away from the true from the data collection policy, your reward model can go just more and more off. And this is not something that you can just fix by trying to do good hyperparameter tuning and model selection over here, because all your data is around this area. Right? There's just not enough data for you to tell whether your model is good or not. Question?
So, for example, if you've got a current kind of mediocre system, it's going to generate mediocre responses, and you'll get some reward for them. And so the simulator will just predict how good the responses are for mediocre responses, but then like optimizing the mediocre response reward may never get to the very good solution.
Yeah, I think it's along those lines, but I think a more explicit example is that yes, like you have the data you get is depends on what kind of policies, like for example a mediocre policy, right? But presumably, like here, the responses we typically use is a base policy, like a pre-trained policy. It's still like spitting out like reasonable words, sequence of words, and so on, right? But when you train this reward model, you're training only on those kind of sequences, right? So there's actually a chance that there may be like a little glitch in your reward model that, for example, maybe you can just spit out an illegal sequence of tokens that just isn't even natural language, but it like hacks through the reward model and achieves a super high score. Right? So those kind of things is like something that you cannot test when you only look at for example, the fitness score, based on this data. Okay, question.
So I think before reaching the auto distribution regime,
okay,
there's another regime where basically between let's say KL of 10 to 40,
what
happens is that you're not over-optimizing reward, you're still improving reward.
Right.
Still hacking the reward in the sense that you have other capabilities in the model that you're losing. So generally, we don't operate in that out-of-distribution regime ever. Like we don't want to go there. We actually way earlier.
Yeah. So I think that's getting like really to practical like in practice like which regime we're actually in. And as I said, I really have no knowledge of like what happens in LLM practices, and this is really meant to be like sort of a example of like generically what's happening, right? And I should say like this figure can also be misleading to some extent, because this is somehow saying that like our learned reward function always overestimates. That's generally not going to be the case, right? And this is only showing one direction of changing the policy. Like maybe in a different direction, your reward model like underestimates, or sometimes it overestimates, sometimes it underestimates. Who knows? So that's actually the part of the difficulty. But in any case, like so far, I think what I've been saying is just pretty obvious truth that if you take it at a general level, like it should be true, right? And the point I really want to make, and this brings me to the main thing I want to do in this talk, is that really if you look at the example like this, you will realize that generalization in the decision-making setting only happens to policies that are in some sense close to your behavior policy, right? And in fact, like here, in this paper, closeness is measured by KL divergence. But in fact, as we'll see later, the more appropriate terminology is actually generalization only happens to policies that are covered by behavior policy. There is a subtle technical difference between closeness in distribution versus coverage, right? But the real question is like, how do we define coverage, right? So for example, is KL a good coverage definition, or some other probability metrics, or what, right? And let me finish this and get. And it turns out that as we will see, what happens is that the kind of algorithm you use have an intimate interplay with the kind of notion of coverage you can achieve. So and that's what I'm going to talk about is like, what kind of coverage we can hope to achieve and what kind of algorithms achieve them.
So intuitively, what you would want to happen is a very small region under the behavioral policy to be a very large region under kind of the optimization regime, right?
Right. So yeah, that's what I'll get to. It's like essentially you will hope to define a notion of coverage that allows you to optimize over a wide range of policies, right? But we'll see like some of the most intuitive and natural definition of coverage actually constrain you to extremely small areas around the behavior policy that it's almost not going to do anything. So you have to introduce additional assumptions to strive for more lenient notion of coverage. Okay. So before we get to more concrete results, let's just quickly go over the framework for decision making. And as I alluded to, I'm more familiar with just modeling everything as RL problem. So based on with a few idealized and simplification assumptions, we're going to think about episodic RL problems, where in each episode you make an observation, take an action, get an immediate reward, and observe the next observation, and so on and so forth. And this repeats for a certain number of time steps. Let's say it's the horizon. Okay, and if you want to cast the RLHF in this example, the first observation would be the prompt. It could be random. Well, it is random, and each action is just the random token. And the intermediate rewards are 0, and at the very end of the day, you receive a final reward, and that's the reward you're trying to optimize. And in the standard RLHF setting, all those intermediate observations is a constant symbol. They don't, have any information, because when you're spitting out tokens in your response, nothing happens, right? So this is actually a system with fully deterministic transitions, and only a big signal is the only signal is the random reward at the end. Okay, and one side comment is that you can actually model RLHF also equally as just a one-step process where h equals 1, except that your action is now a combinatorial object, which is the entire response. And turns out that for many of the algorithm and analysis we'll do, these two views are actually equivalent, and we'll see that. Okay, so and a policy pi is generally a mapping from observed history to the distribution of reactions you choose. And when we say we follow a policy or we run a policy, what we mean is that every time we're seeing a history and we're deciding what next action to take, we draw the action randomly from the distribution of actions that the policy tells us. And the performance metric we're typically interested in RL is this expected return. Given any policy, when we commit to a policy, when we run the policy, it gives a well-defined distribution over the entire trajectories, and we're interested in the expected total reward for this distribution. Okay. And the OPE problem that I just mentioned, which is closely related to whether generalization happens to a policy or not, is to estimate JPi, this performance measure, discounted return, using data episodes collected by a different policy, pi b, or the behavior policy. Okay. Okay. So the very first question is like, if you think about the kind of things we're trying to do, this is really analogous to holdout validation in supervised learning, right? You run something on training data and you try to evaluate it on test data. So the very first question is like, can you just do it without introducing any additional assumptions and get unbiased estimation of JPi, only using the test data itself without any additional help? Well, it turns out that you can, and it's based on importance sampling. Okay, so there's a long history of importance sampling statistics, and even its usage in RL dates back to 2000. And the rough idea is that importance sampling requires first that your behavior policy is not deterministic. Your behavior policy is actually randomized. And essentially what it does is that if your behavior policy is randomized, in the data you will take random actions, and some of the actions will just happen to match the action that your target policy wants to take. Right? And roughly speaking, super informally, you're essentially just discarding all the data points where the actions don't match, and only keep around actions where the actions just randomly match. Okay? So this is actually it's very simple, but surprisingly effective. And in many industrial applications, such as recommendation systems that uses contextual bandits, this is the way that you use for model selection and evaluation. And when you use it in the sequential decision-making setting, it doesn't require any kind of Markovianity, which is a big advantage, as we'll get to later. But the problem is that these kind of algorithms, estimators, typically give you exponential variance, right? Because if you think about what happens in the sequential setting, it's essentially saying that, for example, if my target policy wants to take a sequence of red actions, and my data policy is like random, sometimes it take red, sometimes take blue, as long as there's a single blue actions in the sequence, I need to discard the trajectory, right? So therefore, in general, like the amount of trajectories I'm able to keep around will be exponentially small. It's an exponentially small fraction of the original data set. More technically, the importance sampling estimator in its most basic form is simply the total reward in a trajectory multiplied by the cumulative product of what we call the action importance weights. And this thing can generally have an exponential variance, even if pi and pi b are not so far away from each other at a per stat level. Okay? But at least like this is an unbiased estimator, and it gives us an example of what I mean by a coverage definition and an algorithm that achieves that, right? So according to the importance sampling estimator, any policy that gives you a sufficiently small cumulative importance weights is considered covered. And you can accurately evaluate it, okay? And that's correct. And the only problem, as I mentioned when replying to the earlier question, is that if you only constrain yourself to policies that have small importance weights, that's a very, very, very small neighborhood around the behavior policy. So that doesn't leave you much room for optimization. And that's why we are interested in seeking more generous notions of coverage. Okay? I was a little ahead of myself, and this is the point I want to make, right? So basically, why do we care about coverage and think about OPE? Or it's because evaluation is often the basis of optimization. Now, one thing, a side note is that when you think about evaluate and then optimize, typically the way many people think about it is that, well, if you have data that covers every single policy you want to evaluate, then you're able to pick approximately the best policy. It turns out that doesn't have to be the case, right? Even with an arbitrary data distribution, there are plenty of ways you can just regularize your algorithm so that you only focus on policies that are well covered, right? But the problem is, again, like if you have more lenient notion of coverage, you have a larger range of policies that you can compete with, you get stronger guarantees. Okay, so remember, this is the importance sampling. It's like a baseline, but it's a not very satisfactory baseline, right? And therefore, we strive for a better notion of coverage. So, and if you think about it, like this is this notion of coverage given by importance sampling is super unsatisfactory, even if we think about super toy problems we encounter in our research, right? So, for example, suppose I'm in this super simple grid world where the task may be just for some navigation, right? And let's say my behavior policy is taking this zigzag route, right? And I've collected data to know, what happens in each of the grid. And I want to now evaluate the policy by going straight down. Okay, so there's like action mismatch, but if you only focus on the state occupancy, then clearly I should have all the information I need to evaluate the red policy because I've visited every single each of these grids, right? But based on the coverage notion that given by importance sampling, it says that no, like these two sequence of actions is different. So you know nothing about what's going to happen with the red sequence of actions, and that's apparently ridiculous, right? And so. So obviously, like, yes, exactly. This is exactly what I'm getting to. It's like, so how does RL work, right? So far, like, there has been like like many years of like deep RL research, and what's happening in there? Well, what's happening is that we leverage Markov assumption. That we know that this is a Markov process. That once you're in a grid, your current location is a Markov state. That your future evolution has no dependence on the past that leads you there. Right? And with this assumption, previously we say, okay, we have observations. Then the Markov assumption says that, okay, now we make the assumption that these observations are states. Right? Condition on the state, the future, and the past is conditionally independent. And once that's the case, there are like a plethora of like algorithms we use, and some of them connect to empirical algorithms we use in practice that actually give you much better, when you analyze them, they give you much better notion of coverage. let me finish this part and get to. So for example, like, in theory, one thing you can do is that there's this very important notion called value functions. If you know RL, like this notion should be very familiar, and it satisfies the well-known Bellman equation, which is a recursive relationship. And in learning, one thing you can do is that you can just try to estimate the Bellman error, which is the temporal inconsistency of a candidate function, and try to minimize it over the data. And if you do that, and let's say you minimize this function, take the value function, learn from it, and use that to predict the return of the target policy. So the target policy is shown over here. So this pi is the policy you want to evaluate. It turns out that the analysis you do will show that you no longer need to pay the cumulative product of importance weights as the notion of coverage, but instead you only need to pay one-step action importance weights as well as the ratio between state occupancies. Right? So for example, in this case, if I've occupied in my behavior policy, I've explored left half of the maze, then if your target policy only visit like these states, that would be perfectly fine.
So this assumes that not only is there a Markov process, but that it's visible, state is visible to the algorithm.
Yes, totally. Well, so yes, totally, yes.
The issue that the set of actions might be itself exponentially large, right?
Yes, that is, yeah, you're all right. No, like all of those points are right. So we'll address some of those, in the rest of the slides.
These are for all statements, right? Like for the latter condition, for all OH, right?
For all
every OH, like the ratio needs to be small.
Well, okay. So first of all, this should be tau h, the history. Second of all, yes, there are technical definitions you can use. If it's for all tau h, that's a standard condition we use. But it doesn't have to be that. Actually, you can just look at its second moment on data. So that's a weaker definition, but I think many analysis you can use that weaker definition. So you don't need to use infinite norm. But that's kind of like a minor technical detail. Yeah. Okay. So, and there are improvement, for example, you can leverage based on the function class that you use to, fit your value function. We'll get to that later, but if you're into RL theory, you may recognize this improved version, but otherwise it's okay to ignore it for now. Okay, so I'll skip this. This is really a full RL theory tutorial. I'll skip this, but just to give you some intuition for why learning the value function actually helps you achieve this better notion of coverage in the MDP setting, right? So really what we're leveraging is that this notion of state is information bottleneck. Once you condition on the state, the future and past become separate, right? So what we're doing is that we're minimizing this objective, that is the Bellman error of a candidate value function, and this objective is only a function of state, right? So although we're training it or minimizing it under distribution of histories generated by the behavior policy, and error decomposition tells us that what really matters is that you want this quantity to be small under trajectories generated by the target policy, okay? But although that's the case, you don't really have to transfer error from full trajectories to trajectory distribution over here because of the existence of bottleneck. And the very fact that the loss function itself only depends on this bottleneck, right? So it turns out that only the marginal distribution of the state matters. And as long as the marginal distribution over the state covers the marginal distribution that you would observe under the target policy, you're fine. Okay? And by the way, that's a super short summary of years of research in RL theory. And if you're interested in getting to know RL theory, especially in the offline setting, from this angle, we recently have a survey paper or rather tutorial paper under review for Statistical Science Journal that I would recommend checking out. Okay, so so that's good, except that in a lot of the real problems, we don't have Markov systems, as you exactly said, right? In particular, if you think about applying this framework to large language models and RLHF, you don't have a state, right? So every single token is just an observation. It's certainly not Markov state representation of a summary of the whole history. So we have to go back to the setting where you have observations and they're not state. Except that here is a simple solution, right? Every single non-Markov problem can be converted into a Markov problem if you just simply define the entire history as state. Problem solved. Okay, question? Yeah, exactly. So, but are we done? Well, the thing is that the number of states, yeah, that's a great point. But the number of states is never a real problem, because even in the previous setting, like when we incur something like the occupancy, you don't necessarily pay the number of states, right? For example, if pi and pi b is the same, this quantity is just 1. And you can drift away from that distribution and still have like a relatively small quantity. So this quantity does not explicitly depends on the number of states. Okay, but it's, yes, like something along those lines is the problem. So do we see what's the problem? So the problem is the following. Remember, like if you apply the previous framework, what you will pay is the density ratio between the marginal state distributions. Okay, now if you say that the state is the history, we're now paying the ratio between histories. Okay, so this is referring to the probability of a history under the target policy over the probability of a history under behavior policy. And guess what this ratio is? This ratio is exactly the cumulative product of importance weights. Okay, so you basically, if you apply this framework, you go back exactly to importance sampling. So it's saying that yes, the usual story in the MDP case is that, say, by importance sampling is good, that it doesn't require any function approximation assumptions, but it has a very strict, unforgiving form of notion of coverage. Whereas if you leverage the Markov assumptions, you get a much better notion of coverage at the cost of introducing function approximation biases and so on and so forth, right? So here you're getting the worst of both worlds. You're introducing function approximation biases, and you get a notion of coverage that is as bad as importance sampling. Okay, so that's the thing. Okay, so and in fact, out of curiosity, I actually go and check some empirical RLHF papers to see what is this value in RLHF experiments. Well, it turns out that for some good policies we train, when you evaluate this, it's actually at the order of exponential of something like 25. So this is like ridiculously large, which says that if you only look at the action probability ratio, it's not a proper notion of coverage that explains the success of RLHF policy in practice. Okay?
For this experiment, we just think of pi and pi b to be true trade, like good trade.
No. So pi b is the base policy that collects the data for which you learn the reward function, right? And you keep doing, you fit the reward function, keep doing training on it. At some point, you stop it, you get a good policy. Now that's pi, and you look at these. Okay. So, and this is the general problem. Okay. So there are a few ways that you can try to go and address this problem. Go ahead.
What's the practical value that wouldn't be a problem? Like, so each of the 25 is a problem. Like, what's the range? I'm not very familiar.
So the problem is that there's no problem in practice. Practice, everything works out fine. And it's a problem for me because I want to understand the theoretical justification or the theoretical understanding behind it. How do we explain that we are able to train a policy so well based on reward fitted only on the behavior policies data? And all I'm pointing out is that the understanding based on using like state density ratios for non-Markov system, just doesn't apply here.
So what I think is happening is that your guarantees on generalization require amount of data that's proportional to this amount.
Yes, exactly. That's the thing. It's like the sample complexity in the typical guarantee we need will scale at least linearly with this quantity. And if this quantity is this, like, apparently that's way beyond. Yeah. But
I just realized I'm a little bit confused about your setup here. So generally in RLHF, you'll first collect a lot of human preference data.
Yes.
And then you learn proxy reward functions.
Yes.
You don't just take a set of trajectories from your original base policy. You keep taking more trajectories as you train.
Well, that's yeah. Okay. So there's I think what you described. There's the difference between what we call offline learning and online learning. So in the pure offline learning setting, you use the base policy to collect responses, annotate them, label them with preference data, and that's it. And all the remaining training. And I think some of the earlier and standard RLHF framework actually takes that setting. That is, we are able to train good policies using that setting. But you're right, like maybe a much better way to do it is actually if you have on-demand access to the annotator, then as you train policies, you should generate new responses from your later policies and ask people to label them. And that's what we call the online setting. Actually, the next speaker will talk more about the online setting.
I think that is done in practice, but I was asking about something in between, which is the way that this is. This was originally presented, I think. So you collect trajectories and human preference judgments, and you keep collecting new trajectories according to the policy, but you judge them from the proxy reward.
Yes, exactly. So, that's what I'm talking about here.
Right. So the online learning is not that you get new human annotations. It's
right,
that you get new proxy annotations.
Right.
So I think the thing that has to generalize for this to work is the proxy.
Right. So the
proxy generalizes out of distribution.
Yes.
Then you might be fine. And you don't have the
right. So all I'm saying is that this particular concrete theoretical framework doesn't explain that success.
It doesn't explain why the proxy would generalize that.
Yes. Exactly.
So if you can shave 25 to 8, would that be?
But it's still exponential. I don't know. Like this is like just vibes, right? Because in theory, everything is asymptotic. Like no constant number matters. This is a constant. I'm just saying, like it gives you vibes that it doesn't. Like as I said, I know nothing about the concrete, like really like empirical understanding of what happens in the LLM space. Only using them as sort of like thought-provoking examples. Yeah. Sorry that I can't really, get into the details of, RLHF. Okay, anyway, so, one direction that you might go with this, which I think is a very promising direction, but we haven't studied this, but I'll just throw it out, is that, so part of the reason that you have to say is that it's like, it got to be the case that this actually, this notion of coverage or the upper bound you obtain with it is simply a loose upper bound, and you want to tighten it. And presumably, if you're tightening the right way, you actually get to a reasonable bound that explains the practical success, right? So as I alluded to earlier, this bound only talks about the probability ratio, ignores everything else. And we have an improvement based on, for example, the function approximator you use, right? In particular, in some very simple and primary settings, suppose the function of space you use to fit the value function is linear in some feature, okay? And so it turns out that you can actually improve this bound by quite a lot. So what you get is this coverage not in the action probability space, but in the feature space. So now instead of like having to cover exactly the same actions, you not only need to cover feature directions. Okay, so basically it gives you some kind of generalization benefits that if two actions points to the similar directions, even if those actions are completely different, they may be considered you may get well covered in this more improved notion. But of course, like we don't know anything beyond the simple linear case, so you may ask the question. And of course, like when you have these complex long sequence data, making the assumption that a good encoding to begin with is just completely ridiculous, right? So you may as well just ask, what if I replace this feature space from linear to say a transformer or something like simpler, along those lines? How does an upper bound like behave in that case?
Does your algorithm have to know phi or just?
So to obtain this particular bound, yes, you have to know phi. So that's why I say like this is a super toy, idealized theory. Okay, so that's what not the approach I'm going into, but at least it gives you the sense of the kind of direction one direction you can investigate to address this issue. So the kind of direction we work in is a different direction, and I guess I have 15 minutes. Yeah, I think that's good because I now eventually get to what I work on, but I think that's actually good because the actual work I did is like very technical, and given this is more of a mixed audience, I'll try to give you just a taste of where we're going. Okay, so the direction we're going into is that we want to. So basically, you need to introduce additional assumption anyway, right? So instead of introducing the assumption on the agent or your function approximation, another direction is that we make no assumption the agent and its, say, function approximation and so on and so forth, but instead make some common assumptions on the environment, on the dynamics itself, right? So can we actually address the problem by making assumptions on the process itself? And when we think about non-Markov environments and processes, an extremely common setup and formulation is latent variable models, right? So in the case of sequential decision making, this will go to POM DPs, and this is a very natural model because for many, say physical process out there, when we build models for them, we build them based on, unobserved variables that will better explain the process, observable process out there. And POMDPs are even also used in early research of chatbot and dialogue systems. And sometimes like people try to map latent states onto say something like user intention. Right? So this is, at least you may say it may be a little bit far-fetched stretch for the current research, but I think this is definitely, one natural, another direction of investigation. So formally in a POMDP, what happens is that every time step, the nature actually generates a latent state, which you don't observe. And from the latent state, it emits an observation that you actually see. So in this way, the observations themselves no longer need to be Markov. And then you take an action, and then you receive a reward, and then there's a latent transition that happens. Again, you don't observe it, but then you receive an emitted observation from it, and so on and so forth. Okay? And for this particular work we did, we're restricting ourselves to memoryless policies. This is a big restriction. We're relaxing it in follow-up works. And again, like just to remind everybody, the goal here is to come up with a good estimate of a return of a target policy using data episodes collected by a behavior policy. And the key thing here, and to remind everybody, is that we want a linear notion of coverage, right? So instead of like trying to define coverage as probability ratios over entire histories, we want something that is similar to what we obtain in MDPs, right? So in MDPs, the kind of coverage definition we get is the distribution of a marginal state distribution, okay? So here, we also have a notion of state, right? It's the latent state. So naturally, you have the question of, can we actually achieve something like coverage, an estimation guarantee, where the coverage parameter is, for example, the probability ratio of marginal distribution of the latent state. Okay, so that's our goal. Okay, so and if we and to achieve that, apparently we're going to take some lessons from the MDP analysis, right? And remember, in MDP setting, the key object that we model that gives us the state density ratio is this notion of value function. Well, it turns out that for memoryless policies in the POMDP setting, you can also define this value function over the latent state space. And if you can directly learn it, let's say minimize is a Bellman error, you would directly achieve our goal, right? Because then you will get coverage over the latent state. And the only problem is that this notion of value function that is defined over the latent state is not something that you can directly use because the latent states are not observed. Okay? So the key here, and what we did, is to come up with proxies of this value function that actually more or less behave the same. Okay, so just give some intuitions, right? So this is sort of a illustrative figure where it shows that in the MDP case, if you leverage the fact that the state is an information bottleneck, it allows you to do error transfer without paying coverage over entire history, right? But in the POMDP setting, the problem is that if you still define value function as a function of latent state, it's not usable. The only other notion of value function, as we see, is that you define history as the state and define value function over that. But the problem is that if you use value function as that, it breaks this information bottleneck. You no longer have this latent state as the bottleneck that blocks the past, the influence of the past into the future. Okay, so if you can't define value function as a function of state, you can't define it as a function of history. Here's a wide idea. We define it as a function of future. Okay, so we define value function as a function of the random future. Now, this may seem like extremely crazy, but it turns out that it actually has a long history of related ideas in the literature. Okay, so first, technically, the way we define it, I don't think this really matters, but for those who are interested, the way we define it is that the future-dependent value function is any function that is a function of the future observables, such that when you take its conditional expectation, conditional on the state, it's the same as the value function defined over the latent states. Okay, so in this particular sense, it serves as a proxy of the latent value function. Now, why I say that there's a long history of related ideas in the literature is that if you look into the literature of time series data, stochastic processes, there's a long history of using future predictions as alternative state representations. And it's studied even in CS-related areas, is studied under the name of observable operator models, predictive state representations, stochastic multiplex, SMA, I forgot the name, but yeah, so there's a like automata version of it, in that community. And there's a very nice survey paper in 2015 that summarizes the connection between all these areas. Right, so the basic idea is that because of the existence of the latent state as a bottleneck, information bottleneck, when you look at the distribution over all possible future variables, it actually has a very strong low-rank structure. Because the possible distributions over all the future variables can always be written as the dot product between the conditional distribution over future condition on each latent state, and then the distribution over this latent state, right? So that like decomposition is what leads to this idea. Okay, so I'll give like super quick intuition for why learning this future dependent value function actually gives us a very good notion of coverage. Okay, so remember this is the illustration that we had in the Markov case, where all your value function only depends on the latent state, and that's why you can have a very nice error transfer that transfers from the marginal distribution over the latent state to here. Okay, so now what we have is that our value function now depends on the future. Okay, so ideally, what we want is that we want to minimize its temporal inconsistency conditioned on the latent state. If we could do this, it will be equivalent to, it's as if we observe the latent state directly and learning from there. So we achieve all the guarantee we want. Except that we can't do it because we can't do conditioning on the latent state. This is an unobserved variable. So the only thing we can do is that we need to replace this conditional variable with something that is observed. Okay, so the variable we choose, the variable we choose is that we just use the entire history. Okay, so now this is a little bit warning because if you use history, now this is a function of history, then maybe you think, okay, maybe I need to pay, the coverage coefficient in terms of probability ratio over history. But that's not the case because the loss function, the variable we depend on over here, are all in the future. And as you can see, like it's separate from the history and they go through the latent state as the bottleneck. And that's roughly, give you a sense of why we're able to achieve something like latent state coverage. Okay, so more technically, the actual Bellman error we estimate can be written as this particular thing we want to minimize, dot product with the belief state, which is the posterior distribution over this latent state given history. So essentially what happens is that ideally we want to minimize this function as a function of latent state. We can't do it. The thing we can do is that every single trajectory give us a linear measure of this function. And we're making sure that that linear measure in expectation is 0. So if you have a function you want to minimize, but every time you only get a linear measure of it, and you make sure that the linear measure is 0, what's the condition you would want about those linear measures to guarantee that eventually you get that function itself to be 0? Anyone? Yeah, exactly, right? So for example, if you have like just 2 latent state, every time when you get a linear measure, essentially you're approximately shrinking the possible space to nearly one-dimensional, right? So if you get another linear measure in a approximately orthogonal direction, eventually you get functions that are just 0 in all directions. So that's roughly speaking give you the intuition. So now instead of covering the latent state, we need to cover all directions in the belief state space, which is like which are like distributions over latent states. Well, if you get into the technical details, it turns out you don't even need to do that. All you need to do is to make sure to cover this the marginal distribution induced by the target policy. Okay, so now this is the technical proof, the guarantee that we achieve, but I'll not go into detail over here. So just one more thing to mention is that so this gives us this notion called a belief coverage. This is a novel coverage condition we identified that is tailored to the structure of MDPs and our algorithm is able to achieve finite sample guarantees under this notion of coverage. And one small thing, one interesting thing to observe is that all of this work is making the assumption that we can model this function called future dependent value functions that satisfy this equation. And it's actually like after the very first paper, we realized one thing is that this function may not even exist. Okay, so in particular, if you stare at this equation for a long time, you realize that there are situations, for example, if you have two latent states such that their future observable distributions is identical under the behavior policy, but their value is different under the target policy, then this equation will have no solution whatsoever. Okay, so that's the interesting thing, is that it turns out that you need some additional assumptions to make sure that even this equation has a solution and have a well-bounded solution. So and this is the other condition we identify. There's a sufficient condition we call outcome coverage that makes sure that guarantees that this equation always has a well-posed solution. And the kind of idea is exactly, is kind of alluded to in this example, is that if you have states that the target policy don't distinguish between them, then it's okay that your behavior policy don't distinguish between them. But if those two states have very different values on the target policy, then you need to make sure that your behavior policy also excites those events that tells you the difference between those two latent states. Okay, so but what's really interesting is that this notion of outcome coverage is very symmetrical to the behavior coverage that we see, right? And this is what is very new and different from the MDP case, because in the MDP analysis, you only see this notion of coverage from the direction of history, from initial state to the current time step. But now we have this new coverage condition that's talking about from current state to all the way to the future, that exhibits a very interesting symmetry between past and future. It gives you the vibe like, actually the analysis should have been this like all the time, and MDP is just a special case that eliminates part of the symmetry. Okay, anyway, so we have some extensions about memoryless, beyond memoryless policies, but there are still more things to do when you have rich, policies that have a rich memory update. Okay, anyway, so that's it. Oh, I know this is not a talk that is really related to RLHF or anything, but hopefully give you some thought about how we think about generalization, distribution shift over long sequence data. Okay? Yeah.
Questions?
Yeah, go ahead.
Is this like the belief state representation of particular special case of the features of the V function?
Well, it's
does it imply the linearity on the?
So no, it doesn't. So what's so basically this notion of belief coverage, you can so the thing is that when you look at the condition, right, it actually looks very similar to this linear form, but the linearity comes from very different reasons, right? So here linearity comes from assumptions on the function class, but there the linearity only depends on the POMDP dynamics. It has nothing to do with your function class. In fact, if you have knowledge of function class, you can further refine that one as well, just as how you refine this one to this one to this.
Right, but that's what I'm saying. The dimensionality of that the belief state.
Yeah, the dimensionality is number of states. Yeah, it's number of hidden states.
The size of the state space.
It is, but the thing is that again, it's just similar to when we talk about the marginal state distribution, we say that when you pay this quantity doesn't necessarily scale with the number of states. Right. Similarly, if you look at the definition of belief coverage, again, it doesn't necessarily scale with the dimension as well, right? The simplest example is when you have pi equals pi b, then it's just 1, right? That's a sanity check, but it gives you it's too long, but it gives you at least it's a good sanity check to make sure that this is well behaved. So you don't have to pay like the dimensionality in some benign cases.
Is there like a sense in which any of these metrics? So I guess you're trying to find sufficient conditions. So
Right.
Is there like some sense in which these are necessary?
So
I guess if you're somewhat worst case with respect to how you collect.
Yeah. So as I said, like these are never really necessary in the sense that we already know that, for example, the condition like this can be further relaxed if you have additional structure in your value function class. Like it's just like less interpretable. So like we make this just for the purpose of interpretability. But recently we are doing some follow-up work that are actually looking at some cases that are that we do actually see some hardness results, right? So for example, like one severe restriction of this work is that we assume both behavior and target policies have to be memoryless. So it's like, what if like my policy just becomes fully history dependent? Well, guess what? Like there are very simple information theoretic lower bounds that says like, at least for the kind of algorithm we're thinking about here, that is like model free algorithm, you don't learn a generative POM-DP model. As long as that's the case, no algorithm can handle the general case in the worst case. So which means that even if you consider fully history dependent policies, you need to inject additional assumptions in one way or another. Yeah.
I can ask one more question. So I think to add to the kind of discussion that we had in the middle of the talk, for the RLHF, generally we're interested in policies that have a KL divergence.
Yes. Right.
The base policy.
Yeah.
So I think that number that you calculated is like probably 3,000. And I'm wondering if that,
well, I think it's way beyond 3,000, right? It's exponential to the power of 25. That's like
because like the KL
yeah.
divergence is 10, so the dog
Like a few thousand, yes. Yeah. So you're saying like in that range, maybe density ratio is still, yeah, maybe totally, yeah. But like if I have the yeah, but I mean, but I agree, yeah.
Cool. Let's think non.
Thanks.
We're back at 2:15.